When studying linear algebra, we have seen that a linear transformation can be represented using a transformation matrix. Now we want to understand more about the linear transformation and to characterize better this function, determine the pivots, the constants of this linear mapping. In fact, let's take f as an endomorphism. We want to find a particular basis B in V such as that its transformation matrix can be written in the simplest form. We can define a real number, an eigenvalue, if and only if exists at least one vector in V such as, applying the function to the vector V, we get lambda times the vector itself. So for these particular vectors V, the function just scales their magnitude, but doesn't change their direction. So given lambda, every vector that satisfies this condition is said to be an eigenvector. So the scaling factor is the eigenvalue, and the vectors that have satisfied this property of f are said to be eigenvectors. Since the endomorphism can be written using the transformation matrix, we can say that A multiplied by the vector V is equal to lambda V. Again, the mapping changes the eigenvector magnitude, but preserves its direction, because here lambda is a scalar, a real number. It doesn't change we can say the form of V. This can be seen using this graph. This picture represents this linear transformation, which can be characterized using this transformation matrix. We can see that this linear transformation preserves the direction of the vectors parallel to its eigenvectors. And the eigenvectors are these two. This one stays in this diagonal, in this diagonal, and in fact you can see that every vector that is parallel to this diagonal, and which is in pink, doesn't change its direction, just scales in magnitude. Again, here the pink vectors refer to the eigenvalue equal to 1. We can say the same for the eigenvalue lambda equal to 3, in which every vector parallel to this diagonal, the blue vectors, are just scaled, but the transformation doesn't change their orientation. So, as you can see through this formula, this is a note, these formulas are always satisfied for every eigenvalue by V equal to 0, the neutral element. So that's why we don't consider it in the definition of eigenvalues and eigenvectors. So let's retrieve our F endomorphism. We define the eigenspace of F given some an eigenvalue lambda as the set of autovectors. Here it's that's an error. Are the eigenvectors of lambda, and we add the null element. So the eigenspace for the eigenvalue lambda is equal to all the vectors in V, such as this relationship is proved. It can be proved that the eigenspace is a vector subspace. Now let's move on talking about one other concept, and then we will return talking about eigenvectors, eigenvalues, and eigenspace. Let's take a generic linear mapping that maps V to W to generic vector spaces. We define the kernel of the function phi as the set of vectors where the function applied to those vectors it's equal to the neutral element of the W vector space. The kernel is this cluster of vectors that goes through this linear mapping to the zero element of W. Of course, it always holds that the zero in V is an element in the kernel of phi. In fact, phi of the zero is still equal to 0 because it's a linear map. Also, the function is injective if and only if the kernel of the linear map is the neutral element, is 0. Again, if this equation would not hold, then it means that two elements in V go to one element in W. So the function, of course, will be not injective. With this notion in mind, we can say that the eigenspace of 0, of the eigenvalue 0, is equal to the kernel of F. In fact, if we take lambda equal to 0, we are saying that F of V that equals 0. It's the same definition of the kernel. If we take a generic eigenvalue, lambda, then if we subtract F by lambda and the identity linear map that goes from one vector to the same vector, then its kernel, the kernel of this function, is equal to the eigenspace for a generic eigenvalue. We can prove this relationship because in a very easyful way. If the generic vector stays in the eigenspace of lambda, it means that this relationship holds. So we get this, and we can write V as the identity linear mapping applied to V. It's the same. So we are saying that F minus lambda, the identity linear mapping, stays applied to V is equal to 0, which is is the definition of the kernel. So V stays in the eigenspace of lambda if and only if the same vector stays in the kernel of F minus lambda identity linear map. When writing this kernel, we are saying that in the eigenspace there are every vector x that is a solution of the homogeneous linear system A minus lambda identity matrix times x equal to 0. We need now to find the eigenvalues, and we can say that lambda is an eigenvalue of F if and only if the eigenspace of lambda is different from the single neutral element 0, thanks to the definition of the eigenvalue. In fact, lambda is an eigenvalue if there's a vector that is different from 0 that holds the definition we've seen in the previous slides. So it means that if the kernel should be different than the only the 0 element, it means that multiple vectors are mapped to the null space, to the 0 vector. So this function that stays inside the kernel must be not injective. So again, this function must be not bijective. But a bijective linear transformation should have an inverse, of course, thanks to the injective property. So if the bijective linear transformation has an inverse, we can associate a matrix that is an invertible. The transformation matrix should also be invertible. But we've seen that from the properties of the determinant, if a matrix is invertible, then the determinant should be non-zero. Here we have the opposite of this proposition. So, if this function is not bijective, then the determinant should be 0. We have found a way to determine the eigenvalues, because lambda, a generic lambda we want to find, is an eigenvalue of our linear map if and only if the determinant of f minus lambda identity function is equal to 0. Of course, this expression can be also written using the transformation matrix and the identity matrix. The determinant can be expressed using the usual notation, and we can see, since the identity matrix has once only on the diagonal term, on the diagonal, and 0 elsewhere, lambda multiplies only on the diagonal terms, and A minus lambda identity matrix is equal to this matrix, in which we compute, from which we compute the determinant, and we impose this determinant equal to 0. So we are able to compute the determinant. We already seen how to compute it thanks to the Laplace expansion. And now I want to show you how to compute the determinant of A minus lambda I. Here there's an error, excuse me. So for A with dimension y times 1, we have to compute this determinant with simple determinant, and we get a polynomial of degree 1, in which lambda is the unknown variable and A11 is known. With a 2x2 matrix, we already know how to compute this determinant, and we get a polynomial of degree 2, again with respect to the lambda, which is our unknown variable. We can do the same for the 3x3 matrix. Again, we get a polynomial of degree 3, because the lambda to the power of 3 comes from this multiplication. So we can say that the determinant of A minus lambda I is a polynomial. And this polynomial is said to be the characteristic polynomial of A, and can be written in this form. Notice again that the polynomial has and the degree n, which is the dimension of A. As we have seen before, if the matrix A is a 3 by 3 matrix, then we get lambda to the power of 3, a polynomial of degree 3, and so on. So the eigenvalues, looking at how we characterize this polynomial, the eigenvalues are the zeros of this polynomial. So we need, we need just to compute this determinant, get this characteristic polynomial, and impose this equal to 0, and find the roots, the zeros, of this polynomial. Let's take a look to this example, the rotation example. In the previous course, when we've talked about analytic geometry, we already seen how to define the transformation matrix of a rotation linear map. To find the eigenvalues of this transformation, we have to compute the determinant of r of theta minus lambda of I. We need, of course, to impose this determinant equal to 0. Again, here is the expression of the determinant. So let's compute it. The matrix is a 2 by 2 matrix, so we get the cosine of theta minus lambda multiplied by itself. And then we have minus sine of theta times sine of theta. So it minus times minus equals to plus. We write the expression, we do this square term. Cosine of theta squared plus the sine of theta squared is equal to 1. Here we get. And the characteristic polynomial can be written in this way. Lambda squared minus 2 lambda cosine of theta plus 1. To determine the eigenvalues, we have to impose the characteristic polynomial equal to 0. This is a squared equation, and to solve this quadratic equation, we have our delta. To solve this quadratic equation, so the square of the cosine of theta must be equal to 0. And there are only two solutions for this. The first case is that the cosine of theta is equal to 0. The second case is that cosine of theta is equal to minus 1. So, in both cases, theta must be equal to 0 or equal to pi. Otherwise, we are not able to find the eigenvalues, real eigenvalues of the rotation. In fact, we can find the roots for the characteristic equation only in two cases, theta equal to 0 or theta equal to pi. If we have, for example, theta equal to half of pi, we can't find real numbers as eigenvalues. Again, in these two cases, the rotation mapping changes the magnitude of some vectors, but preserves their direction. In fact, it's the simple definition of eigenvectors. With theta equals to 0, we can easily get that the eigenvalue is equal to 1. So, the transformation matrix of the rotation can be written as the identity matrix. So nothing changes using theta equal to 0, of course. Using theta equal to pi, the eigenvalues are equal to minus 1. We get the opposite of the identity matrix. Thanks to eigenvalues and eigenvectors, we are able to find the pivots of the transformation, somehow the constants of the transformation. The vectors that are just scaled, but that doesn't change that do not change in direction. In the further sections, we will leverage those concepts to decompose and approximate the matrices and carrying on the most information that characterize that linear map.